Thanks a lot for the nice introduction. Actually, this was basically joint work with Florian, and basically as my master thesis. And yeah, well, in my talk, I would like to give or to present an application that motivates basically high-dimensional distributions or learning high-dimensional distributions on rotational quantities. And additionally, I will present our work that allows learning densities on multiple SO3 manifolds. Maybe to motivate first, why are we actually interested in learning a probabilistic human pose model? So typically there are, I guess, two applications of a probabilistic human pose model. First is more in a VR and AR setting, where one might be interested in generating realistic and likely human poses or even human motions. Second, and this is probably more a task that we're interested in robotics, or in general in computer vision, is we have as an input an image, and we want to fit or estimate the parameters that sort of represent the 3D pose of a human body. And here there are several challenges to take into account. But in general, like this task that we're considering here, basically uplifting from 2D information in the image to a 3D pose, is highly ambiguous. And in tasks like human-machine interaction, it's of interest to actually have some sort of statistical guarantees where actually our human pose or our human body is actually located. For this reason, it's interesting or relevant to also consider the probabilistic model of such an estimation. In general, the challenge of estimating the 3D pose is first, as I said, the ambiguity, which arises from, let's say, the lower dimensional information of an image. And second, if we estimate our human pose, then there might be like some poses that we are estimating might be not corresponding to a realistic human pose. So let's consider, for example, this example where we have this input image and we want to estimate the 3D human pose. If we apply a standard human pose estimator, then something like this happens, where actually basically the 3D constellation of the human body is sort of coherent with the 2D information we got from the image. However, our estimated pose does not correspond to a realistic pose, because as we can see here, the left hand is behind the person's back. But if we now inject some sort of prior knowledge about the distribution of realistic or feasible human poses, then we can actually fix the problem. And in that case, we not only have a realistic pose, but we also have the correct pose with respect to the input image. Previous works typically considered two different terms when we're talking about prior, which is not necessarily just the prior density, but it can also relate to the fact that we inject some prior knowledge in that community. So the first approach is more like that you define some sort of set-based prior, which prevents unrealistic poses. You can, for example, do this by just injecting constraints of the human joint rotations that we're considering, or you can, for example, project unrealistic poses, as we can see here in this example on the left, and to the manifold of realistic poses that was learned from a large-scale data set. However, we are more interested in actually learning prior, as we probably, our community here understands it, in a Bayesian setting, where we want to basically explicitly model the uncertainties that arise from also ambiguities in the input, as we can see in this example picture where the right hand is occluded. But there are several ways to kind of model the human pose. And one very simple approach would be to just predict the Euclidean joint positions of the human body. However, the variation of the human pose is mainly governed by the rotational degrees of freedom of the various human joints, which are then propagated along the kinematic tree of the human body. In general, various joints of the human body can be represented by different rotational manifolds. If we consider, for example, our shoulder joint is a ball joint, which has 3 degrees of freedom, is best modeled in SO3. However, there is, for example, the fist joint, which has just 2 degrees of freedom and is best modeled by a 2-sphere. Or if we consider, for example, the elbow joint, which has like basically 2 orthogonal degrees of freedom, and it would be better modeled by a torus. However, in the computer vision field and literature, people tend to use the SMPL model, which is basically a unified representation of the joints. So they only consider or basically they consider or they represent the human body by 21 joint rotations that have 3 degrees of freedom. And in our work, we also stick to this parameterization, even though in the future it makes sense to also inject more explicit knowledge about the human anatomy. How we start with when basically targeting and learning a density over the product space of SO3 manifolds, we start with a large-scale data set, the AMAS database, which is basically a collection of different motion capture data sets, which includes a variety of different motions and activities. And here, as previously pointed out, the human body is parameterized by 21 rotations of, or by rotations with 3 degrees of freedom of 21 human joints. And this large-scale database has like around 40 hours of motion data, which allows learning expressive priors of the distribution, or like, let's say an expressive distribution that sort of captures what are the feasible and realistic poses a human can have. When basically thinking about how to learn such a high dimensional distribution, we first conducted a statistical analysis of the AMAS database, because we're basically starting by the fact that we could apply some sort of simplification or some hierarchical like basically a decomposition of the joint distribution. However, when checking basically the statistics of this data set with using the spherical correlation coefficient, we figured out that basically for different data sets, as we can see on the right, 2 different data sets have completely different correlations between different joints of the human body. So there is no way to kind of have like sort of a structural or inject some sort of modification or hierarchical density estimation that reduces the number or reduces the dimensionality of the problem. Therefore, we targeted to actually learn the joint density, which is defined over all joint rotations of the human body that is considered in the SMPL model. Our design choice for learning such a density is a normalizing flow, since due to their diffeomorphic character, they ensure that the original density, which is used for, like, let's say, as a base distribution, remains normalized. And we train the normalizing flow in the following way. We use the AMAS database with the large-scale data set, and we learn a normalizing, or we train a normalizing flow using maximum likelihood training. After this normalizing flow is trained, we can use it during inference in 2 different ways. First, we can actually use it as a generative model, basically meaning that we can sample realistic and likely human poses. But we can also evaluate the probability of a specific considered or sampled pose. To give a background about how pose pairs were typically learned in the past, I'm going to quickly talk about different strategies. So for one strategy is basically, okay, we don't really care about directional statistics. We assume our generative model, in that case a diffusion model, learns basically the complicated distribution of the human pose. And so there was one work which basically learned a diffusion model which is defined on Euclidean quantities. However, this does not really inject basically the prior knowledge about the fact that the human pose is highly rotational in nature in a way. So there's other ways that basically also sort of stick to this SMPL parameterization, so rotations with 3 degrees of freedom. And basically the first line of work in that regard was a Gaussian mixture model. However, it turned out that this Gaussian mixture model cannot really capture the very complex and highly nonlinear distribution of the human pose. Then there's other works that, for example, use a variational autoencoder. However, they also have like the Euclidean or assumption in a way that it's not really corresponding to the fact that the human or joint rotations are highly constrained in a way how they can sort of move around. Then other works considered GANs, which does not allow basically depicting the likelihood or the distribution explicitly. And then last but not least, normalizing flows had been introduced to learn the distribution of human poses. However, they were also defined on Euclidean space using the continuous 6D representation of SO3 rotations. So basically there was a need, or was basically a gap, that there was no method which allowed learning joint densities on multiple SO3 manifolds, which we are actually considering in our application. So in our work that was presented at CVPR this year, we model normalized densities on SO3 by applying normalizing flow layers that are explicitly defined on SO3. So basically each layer or each step in the way to transform you from the uniform base distribution on SO3 to the target distribution that we are interested in capturing, each step sort of ensures that we always stay on the SO3 manifolds, and thus our estimated distribution also always corresponds to a density that is then normalized. For this, we use two components, a Möbius coupling layer and a quaternion affine transformation. The key idea is here that the rotation matrix can be described by two of its three orthonormal unit column vectors. And basically, the Möbius coupling layer uses a Möbius transformation defined on a two-sphere, and then conditioned on the first fixed column of the rotation matrix. The second column is transformed to a new point using this Möbius transformation. And this basically results in the fact that we always result at correct, or let's say valid rotation matrices. In a second, or basically the conditioning sequence of this Möbius coupling layer is permuted in each flow layer to allow that we change all degrees of freedom of the rotation matrix, because this Möbius coupling layer is only dimensioned in a way that it basically only changes the degrees of freedom of the second column of the rotation matrix. As a second component, to basically improve the expressiveness of the learned distribution, a quaternion affine transformation implements an affine transformation on the three-sphere, which parameterizes quaternions. And this affine transformation allows moving and scaling the distributions on SO3. And together, they allow learning the highly nonlinear distributions of the rotations of the human joint. And like in the next step, we define the normalizing flow on a product space of multiple SO3 manifolds by connecting the flows for individual manifolds, so for individual joint rotations, using an autoregressive conditioning scheme. And here instead, basically in contrast to previous work, we link individual, or like they typically just link individual dimensions in the Euclidean space. We generalize the typical Gaussian approach, which was originally designed for the Euclidean spaces for normalizing flow, and link the SO3 manifolds in a nonlinear manner directly. And here again, we vary the order of conditioning in each flow layer to allow learning the joint density over all joint rotations that represent the human pose. To showcase the effectiveness of our method, which can in generally spoken be applied to arbitrary fields where multiple correlated quantities, or basically the 3D rotations, are considered, we apply the normalizing flow as a probabilistic model for the human pose. That is, as previously introduced, parameterized by 21 joint rotations of this SLPL model. And yeah, our model can be, for example, applied as a generative model, being able to generate realistic and diverse human poses. Some examples are depicted here. And one key advantage that is actually in contrast to the previous methods that designed the normalizing, that basically designed a generative model, but they did not allow providing an estimate of the likelihood corresponding to a normalized density. And additionally, we not only learn an unconditional prior, but we also support tasks where a conditioning is needed. And now I'd like to give basically the application where we also not only consider learning an unconditional human pose distribution, but also a conditional one. So in that case, basically, our goal is to learn the realistic or the likely human poses given a 2D, given the 2D key points that are, for example, taken from an image. Here, the 2D key points are depicted in black, and they are provided as conditioning to the learned distribution, which is defined over the joint rotations. And in that case, the occluded joints are depicted in red, so they are not given to the model, sort of accounting for the uncertainties that might arise from occlusions also in a real-world scenario. Conditioned on this context vector C, which is computed by an MLP, the uniform distribution of the product space of SO3 manifolds is transformed to the desired distribution, here P of R given C, that represents all realistic and likely human poses. And here, basically, we inject all the prior knowledge that we gained from learning from this large-scale AMAS database. And for this reason, our model sort of accounts for the uncertainties, or basically injects the data-based prior knowledge in a way that it can infer the most likely joint rotations of occluded joints. And here we render 3 example samples of our model, where we also can explicitly, as previously stated, compute or give the likelihood of a specific sample pose. And intuitively speaking, we can nicely see that here our model basically has lower uncertainties for joints that were not occluded, but the model sort of increases or naturally increases the uncertainty of the prediction of the joints that were occluded, as we can see for the larger blob size, which corresponds to the uncertainty in Euclidean space, so basically uncertainty of the joint positions. And this basically captures the distribution that we used for training, so the AMAS database. Typically, it's challenging to evaluate, or I guess the typical approach to evaluate such a probabilistic model is to use the likelihood. However, since previous methods didn't really take into account this strategy or didn't really care about the likelihood of such an estimation, we evaluate our model on various metrics. So there is basically ways that can, in a sample-based manner, they can check whether all the dataset samples were captured in the by the generative model, and the other way around, whether all generated samples by our considered model are realistic. And similarly, we can evaluate in downstream tasks. So we can, for example, see how much we deviate from the ground truth position or from the ground truth human pose if we consider some sort of 2D conditioning, for example, the 2D key points of the human body as presented in the previous example. Or we could also consider the mean per joint position error after basically performing forward kinematics and computing actually the joint positions of the human body. And last but not least, and that's maybe also what we would like to motivate more in the vision community, it actually makes sense to learn to learn densities that are normalized by design to allow computing the exact likelihood. And yeah, with that word, maybe I would conclude my talk. So basically, our work, our contribution was a way that we signed a normalizing flow that is defined on a product space of multiple SO3 manifolds, and we applied this method and benchmarked this method in a probabilistic human pose modeling setting. Future works might definitely consider that our human body is not just composed of several SO3 joint rotations, but it's actually more. There can be more explicit knowledge about the human anatomy can be injected. For example, considering that different joints are not just SO3, but also can be better modeled by a two-sphere or a torus. Second, currently we just consider the pose, so we can basically
you have
apply.
1 minute.
Yeah, I'm about to finish. So apply basically this in human motion estimation tasks, or we could also replace a normalizing flow by more complex or more novel deep learning methods, like, for example, flow matching. And with that words, I would like to thank my supervisors